That's my problem.
You want them.
Okay. The hearing will now come to order. Good morning, everyone. I'd like to welcome all of our witnesses here today. We look forward to your testimony and are so pleased that you're here with us. Today is a very busy day on the Hill, and I'm going to try to be brief in my opening so that we'll have as much time as possible for discussion. However, I think it's important to note right at the outset that based on all of our witnesses' testimony, there's an agreement on the importance of a vital and robust technology development program at NASA and the need to revitalize NASA's existing technology development activities. And I think it's fair to say that all three would likely agree that NASA has been underinvesting in technology development in recent years. Given that two of our witnesses represent distinguished committees of the national academies and the third is one of the most senior officials at NASA, I think those views warrant our close attention. Yet to some extent, our witnesses are preaching to the choir today. This subcommittee has been concerned for some time about the state of NASA's long-term technology programs, and we highlighted the need for action in last year's NASA's Reauthorization Act. To quote finding number 10 from that act, NASA should make a sustained commitment to a robust, long-term technology development activity. Such investments represent critically important seed corn on which NASA's ability to carry out challenging and productive missions in the future will depend. I would also note that the summary report of the Augustine panel that has been reviewing NASA's human spaceflight plans also acknowledged the importance of technology development. And I quote from them, "The committee strongly believes it is time for NASA to reassume its critical role for developing new technologies for space." That is a sentiment on the Augustine panel, which I believe that we all heartily concur. NASA's technology development activities are critical not just to NASA's future, but to the quality of life for all of our citizens and for our nation's competitiveness. Discussions of technology development can wind up sounding pretty wonky, so let me be clear why I think NASA's efforts are so important and need to be supported. This is a photograph. Actually, we were having a recent discussion about this photograph. I know that it's available on the NASA website. It's a picture of a standard commercial airplane that I believe really makes a strong point. As you'll look at it, you'll see some of the most major systems and technologies from research undertaken or funded by NASA. It's an aircraft that many members of Congress, actually the majority of us, fly every single week to come here to work, and yet I bet very few of them, or even members of the public at large, recognize that NASA R&D has made this airplane and others possible. This picture is just one illustration of the impact of NASA's research on our society and our economy. I have no doubt that each of NASA's other enterprises could produce similar examples, and I hope that they will, because it's a story that needs to be told time and time again. So I don't think any of the members here today need to be convinced that NASA should pursue a vigorous program of technology development. Rather, we want to explore what it will take to get such a revitalized program in place at the agency. And in that regard, I want to state my strong belief that we don't revitalize technology development at NASA by robbing Peter to pay Paul. That is, carving out funding from an already underfunded Constellation program so that the long-term technology program can be augmented. I believe this would be penny wise and pound foolish. You don't fix one underfunded program by taking money from another underfunded program and expect anything good as a result. In addition, I suspect that there may not be a one-size-fits-all organizational structure for technology development at NASA, but I want to hear from our witnesses on that topic, as I know that each of them have been thinking a lot about this issue. But it's not just a question of either money or how the organizational deck chairs are arranged. NASA has to be smart and opportunistic in seeking out ways to get its technologies out to the private sector and to other potential government users. That's probably a topic for its own hearing, but perhaps our witnesses here today will have some thoughts on what NASA could possibly do in that regard. So I look forward to an interesting and informative discussion. I'll ask my colleagues today if we can please refrain from asking our NASA witnesses about NASA's response to the Augustine panel, which is scheduled to be released later today. We know that Mr. Scolese is not going to be able to make a comment at this point, and we'll have other opportunities in the future to get NASA's perspective in the next coming weeks. So with that, again, I'd like to welcome our witnesses, and now I'd like to turn to Mr. Olson for any opening comments that he would like to make.
Madam Chairwoman,
Thank you for calling this morning's hearing to examine NASA's efforts to foster and manage the development of advanced and innovative technologies. Let me begin by thanking our witnesses for their appearance today before the subcommittee. I recognize that each of you spent considerable time and effort preparing for this hearing, and in some cases, traveling considerable distances to be here. Please know that this committee appreciates, this subcommittee appreciates your efforts, as well as the wisdom and experience that you bring, and that we will refer to your guidance in the months and years ahead. In the public's mind, NASA is synonymous with highly innovative, cutting-edge technologies. NASA and its predecessor agency, NACA, have amassed a century's worth of remarkable achievements that advance the state-of-the-art in aeronautics and astronautics in many extraordinary ways. Collectively, they have directly contributed to this country's high standard of living, both in terms of directly contributing to a strong industrial base, but also through the unanticipated use of technologies and new and creative applications developed by the private sector. It would be difficult to catalog the number and scope of innovations and the technological spin-offs that have sprung from their work, but suffice it to say that the products springing from NASA's technological genius permeates our daily lives, most notably in the transportation, communications, propulsion, and medical industries. In recent years, NASA has restructured the way it stimulates development of new technologies, moving away from an independent, centralized office towards a diverse, less structured effort influenced more by the needs of individual missions and programs. Views expressed by the external science community seem to suggest that NASA ought to return to the former model. I look forward to hearing from this morning's witnesses on the most appropriate way to perpetuate NASA's enviable record of technology innovation and development. Issues I hope will be explored include how best to broadly reach across the science and engineering communities to stimulate, develop, and assess the most creative needs. To what level of maturity should promising concepts be funded? And how can the most promising technologies be transferred into specific agency projects and missions, as well as benefit the commercial sector? And one last issue: what is the best way to ensure that advanced concepts and technology development efforts have the necessary funding and management stability? I can't think of any other civilian federal agency that has done more to improve our nation's economic and technical prowess than NASA. And it's not because NASA is in the business of advancing our social well-being. Rather, their technological discoveries and innovations developed in the pursuit of challenging space and aeronautics missions have been acquired and adapted by others in many creative products and services. It's the genius of American people that's taken those products and turned them into something for our economy. And before closing, I want to again recognize and thank Chris Scolese for his long service and strong leadership at NASA. Through the first half of this year, you led the agency during an always challenging period of transition between administrations. Your steady hand and candor is appreciated by the Congress and, more importantly, by the men and women who work at NASA. Thank you, Madam Chairwoman. I yield back my time.
Thank you, Mr. Olson. Very well said. I'm glad you're the ranking member. Is there anyone else that would like to make an opening statement? Mr. Wilson?
Thank you, Chairwoman Giffords. And thank you for this important hearing, and thank you for the leadership that you've shown on science and technology. NASA's efforts in the field of advanced concepts and technology development have not only moved to the field of space and aeronautics forward, but have improved our lives through the use of satellite communications, space-based weather observations, and aviation navigation systems. In this time of transition and budget constraints, I believe it is important that NASA continue to have a focus on the technologies necessary for not just the next space mission, but the missions that are in our distant future. Panelists, thank you for joining us today and providing your opinions and expertise to this subcommittee. I look forward to working with each of you, as well as my fellow committee members, as we seek to continue NASA's ability to explore the far reaches of this universe and inspire our country. Thank you, Madam Chairwoman.
Is there anyone else? Okay. At this time, I'd like to introduce our witnesses. First up, we have Dr. Robert Braun, who was the co-chair of the National Research Council's Aeronautics and Space Engineering Board Committee to review the NASA Institute for Advanced Concept. We also have with us today Dr. Raymond S. Colladay, who is vice chair of the Committee on the Rationale and Goals of the U.S. Civil Space Program and chair of the National Research Council's Aeronautics and Space Engineering Board. And we have with us Mr. Christopher Scolese, who is the Associate Administrator at NASA and who has served with distinction as the acting NASA Administrator until Administrator Bolden was confirmed. So welcome all. As our witnesses know, you will each have 5 minutes for your spoken testimony. Your written testimony has been included for the record for this hearing, and when you've completed each of your testimony, we'll begin a round of questions, and all of the members will have 5 minutes to question the panel. We'd like to start today with Dr. Braun.
Chairwoman Giffords, Ranking Member Olson, and members of the subcommittee. Thank you for the honor of appearing before you today to discuss the approaches to strengthen NASA's advanced concept and technology development programs. My name is Robert Braun. The views I express today have been shaped through a 22-year career in aerospace engineering in both government and academic positions. Today I speak to you as the co-chair of the National Research Council's Committee to review the NASA Institute for Advanced Concepts. With your permission, I'd like to summarize my views this morning, leaving sufficient time to answer your questions. I'd like to begin with a summary of our NRC report. NASA established the NASA Institute of Advanced Concepts in 1998 to provide an independent, open forum for the external analysis and definition of revolutionary space and aeronautics concepts. These were concepts that could impact a NASA mission 10 to 40 years in the future. Funded at approximately $4 million per year, or roughly 0.02% of NASA's budget, NIAC operated for approximately 9 years and received a total of 1,309 proposals, from which they made 126 Phase 1 awards and 42 Phase 2 awards, primarily to small businesses and universities throughout the country. At its inception, NIAC was envisioned as a cross-cutting program reporting to the agency's chief technologist. However, in 2004, NIAC program management within NASA was transferred into one of the mission directorates, NASA's Exploration Systems Mission Directorate, and in 2007, NIAC was terminated. I'd like to highlight the following 4 key findings and recommendations from our committee report. 1. NIAC met its mission and accomplished its stated goals. 2. NASA and the nation need a NIAC-like organization. 3. The original NASA implementation of NIAC as an external organization managed above and across the mission directorates was effective. And 4, modifications could be made both within NIAC itself and within NASA to improve the effectiveness of this enterprise. Chief among these modifications would be potentially reestablishing an aeronautics and space systems technology development enterprise within NASA itself. In my view, a NASA strongly positioned for the future should include a blend of mission-focused, near-term, capability-based, mid-range, and discipline-based, long-term technology investments, strategically guided by a continuously engaged advanced concepts program. However, at present, there is no NASA organization responsible for the solicitation, evaluation, and maturation of advanced concepts, or for the subsequent infusion of those worthy concepts into NASA's strategic planning process. In addition, while mid-range capability-based technology investments are perhaps the most critical for a forward-looking agency like NASA, within NASA today, it is this type of technology investment that is actually minimal. In my opinion, this is not appropriate for an agency whose purpose includes demonstrating this nation's scientific and technological prowess, or one that is trying to inspire the next generation of engineers and scientists. A technology-poor NASA greatly hampers our aeronautics and spaceflight development programs. As an example, we cannot continue to rely on 1970s-era technology to land systems on Mars, particularly if we want to one day build towards eventual human exploration. Another example, as stated by both the Aldrich Commission in 2004 and the Augustine Commission this year, we cannot plan a sustainable human exploration program without strong technology leverage. Based on these observations, I suggest NASA establish a formal enterprise to continuously evaluate, prioritize, and mature a strategically selected set of technologies in the relevant environments. Many positive outcomes are likely from a long-term, broadly focused NASA Advanced Concepts and Technology Development Program. Chief among these consequences is the provision of a more exciting aeronautics and space future than our country has today. A suite of game-changing space and aeronautic discoveries are within our nation's grasp. Each of these advances would also serve as a spark to a technology-based economy, an international symbol of our country's scientific innovation, engineering creativity, and technological skill, and a component of the remedy to our nation's scientific and mathematic literacy challenges. Our nation needs to dream big, and achieving large goals is precisely what America has come to expect of NASA. With a stronger focus on technology development, NASA would be well poised to deliver on some of society's grand challenges. This completes my introductory remarks. I'd be happy to respond to any questions you may have. Thank you.
Thank you, Dr. Braun. Dr. Colladay.
Thank you, Chairwoman Giffords and members of the subcommittee. I appreciate the opportunity to appear before you today to address a subject that's very important to the country and has been particularly in my crosshairs for the last 3 or 4 years in the National Research Council and the Aeronautics and Space Engineering Board. Aerospace is one sector where the U.S. remains preeminent, and we have in large part NASA to thank for that. But our future leadership depends on continued investment in long-term advanced technology R&D. In our NRC report on America's Future in Space, we describe the many reasons why space is important to the country, including the recognition that space generates high-end jobs in science, engineering, and math, supplying the workforce for the aerospace sector of our economy that remains the envy of the world. Beyond that, it inspires an interest in technical fields of study that is and will continue to be of vital importance to our economic competitiveness. Sustaining U.S. leadership in space depends on having a sufficiently broad and deep technology base that pushes the frontiers of our knowledge, leads to innovation in new systems, and challenges conventional wisdom with transformational technology. When it comes to truly game-changing technical breakthroughs, a long-term view is particularly important, and such a perspective is almost exclusively the domain of the government. Long-term advanced technology R&D does not happen in industry because the return on investment is years away, and it does not happen in academia without sustained, stable government funding. With that perspective in mind, I'd like to make a few observations. To fulfill its broad mandate in civil and commercial space, NASA should revitalize its advanced technology development program as a priority mission area. Its technology R&D mission should be independent of the major development programs and report to the administrator or some equivalent management structure or governance model to give it the stature equal to the agency's other mission areas. In our report, we refer to a DARPA-like organization in NASA to convey this thought. It should engage the best science and engineering talent in the country wherever it resides, in universities, industry, NASA centers, and other government laboratories. It should be relieved, at least to first order, of institutional requirements to maintain core competencies at the 10 NASA centers in order to ensure that the research can draw on the best ideas and talent wherever it should reside. It should serve not just NASA, but civil space customers, including commercial space and other government agencies or departments, much like its aeronautics program and its predecessor NACA has done for almost 100 years. A comprehensive assessment of the current state-of-the-art of advanced space technology would be helpful to ensure that any new investment in technology R&D would be building on the most advanced technology base currently available. Whatever governance model NASA chooses for managing a technology enterprise, it needs to address technology relevance and transition. The ultimate user community determines that the products of technology R&D remain useful and relevant, And technology transition is a process that must be managed with all the stakeholders involved. In summary, the country expects NASA to be a leader pushing the frontiers of air and space applications and missions as called for in the Space Act. But to do so, NASA needs to replenish the underpinning technology that makes it possible. That completes my brief summary of my remarks, and I'll be open, of course, to questions later.
Thank you, Dr. Colladay. Mr. Scolese.
Chairwoman Giffords, Ranking Member Olson, and members of the subcommittee, thank you for the opportunity to appear today to discuss NASA's technology development programs. NASA has been at the forefront of aeronautics and space research since the early 20th century. The complex research missions that NASA is asked to do to explore the unknown serve as stimulus to innovation. As a result, NASA and its predecessor, NACA, traditionally balanced our technology activities to meet both the needs of our near-term missions and our long-term plans. Recent National Academy reviews of NASA innovation and technology development endorsed increased emphasis on innovative technologies and approaches to achieving broadly defined NASA and national goals. These reports and others suggested that NASA should increase emphasis first in disruptive or game-changing technology, and second in maturing technologies for flight. In answers to the subcommittee's question about the time frame for technology investment, NASA believes the time frame for these early technology activities should be long enough to allow for revolutionary impact, yet not too long so as to mask clear applicability to NASA or national needs, or in the 10 to 20-year time frame. Managing all of the investment areas will require a hybrid of management processes with strong agency-wide planning and coordination. One size does not fit all. Mission directorate investments focused on mission needs will be best managed within those directorates. Early-stage innovation, disruptive, and strongly cross-cutting investments are best served by an independent management structure still responsive to the needs of the mission. With regard to the committee's question on authorization legislation directing greater commitment to robust technology research and development initiatives, 3 examples stand out. In aeronautics, we formulated the new environmentally responsible aviation project to develop technologies related to improving the airspace system to be more environmentally friendly. Multiple collaborations are underway with other federal agencies and private entities to make use of the space station as a national laboratory. And in science, the most recent annual competitions for instrument technology development emphasize cross-cutting technologies. Excuse me. The subcommittee asked how NASA develops and infuses game-changing technology solutions without a dedicated long-term technology program. NASA does invest in a limited number of game-changing technologies through its innovative partnership program and within our mission and engineering organizations. Examples include optical communications and large pressurized composite structures. NASA routinely coordinates with other federal agencies to develop technologies and concepts of mutual interest. The NASA Aeronautics Research Portfolio is strongly aligned with the National Aeronautics R&D policy and plan and the high-level goals of the NRC Decadal Survey. And as mentioned, the Space Station National Laboratory has been made available to other U.S. government agencies, academic institutions, private firms, and nonprofit institutions. For example, NASA funded approximately 250 investigations related to ISS life science research and exploration, many of which leveraged additional funding from the National Science Foundation, the National Institute of Health, the Department of Defense, and the Department of Energy. Our nation has made great progress throughout its history because of the enormously difficult challenges it has embraced. The grand challenge to build an intercontinental railway or the Apollo lunar program not only utilized our best talent, but also created new technologies, inspired generations to pursue challenging goals, created new industries, and ultimately improved our country and the world. Similar opportunities are in front of us now, and NASA most assuredly can contribute. Chairwoman Giffords, I would be happy to respond to any questions you or the other members of the subcommittee may have.
Thank you. At this point, we're going to start our first round of questions, and the chair recognizes herself for 5 minutes. I'd like to start with Mr. Scolese. You've heard testimony from the other panelists about some the recommendations of why this is important and the suggestions that this really matters and it needs to be reinstituted. We've heard about the importance of advanced technology development at NASA, but could you speak more specifically about the attributes of such a program? How would NASA structure a short-term, a mid-term, and a long-range term program in terms of the needs of the agency and its various mission directorates? And also, should we expect to see any changes in NASA's technology development programs in the fiscal year 2011 budget?
Certainly. In terms of the short-term technologies and even the mid-term technologies, we have our programs largely aligned with our missions, so they tend to stay within the mission directorates. And those are moving along fairly well. As an example, in the Science Mission Directorate, we invest about 10% of their budget in technology development. That's where we go off and look at the instruments that we may need in the future, or entry, descent, and landing, as Dr. Braun mentioned early, for going to Mars with different payloads. So for those, as I mentioned in my testimony, we would expect those to stay within the mission directorates. The longer-term technologies, typically we would like to look at things that are cross-cutting, that could affect more than one mission area: aeronautics, science, our human spaceflight programs. Those don't tend to fit well within a mission directorate, and we would think that if we went off to do those, we would take a step back and look at a more coordinated process across our directorates, whether that would be, as Dr. Colladay mentioned, an entity that reported to the administrator, or it would be put into some other organization. I couldn't say at this time. And to your last question, or last part of the question, earlier this year, we recognized, and we recognized before, that our investments in technology have changed. They've changed their focus to a more near-term focus as opposed to the longer-term focus for a variety of reasons. So we asked a team to go off and look at what we could do. So yes, you can expect to see some changes in how NASA does technology in the future.
The next question I have is something that's based on what our recent new administrator said to the general public, and he said that the president tasked him to make NASA inspire young people again. And in that same vein, NRC's report on the NIAC basically went on to talk about that role of NASA's importance for inspiring the public with a spirit of discovery and exploration. So I guess I'd like to start with Dr. Braun. If you could elaborate on your committee's work in terms of what you regard as inspirational, educational, the contributions that NIAC has made, and then turning to Mr. Scolese, I'd like to hear some of the elements in this technology program that we could pull that in, and of course from Dr. Colladay as well.
Okay. In addition to the work that was funded directly by NIAC with the external innovators, NIAC did have a student fellows program and also was very visible in a public outreach campaign. So to address your question directly, I think that our committee felt that NIAC did an excellent job of actually earning positive public support for NASA through its actions, and of inspiring students actually around the country to be a little more creative and to think outside the box. So that was certainly true. If I could add one other point, in my discussions with students on campus, that occurs most days, when I'm not here in Washington, D.C., students are really interested in the future, much farther beyond, say, the next 5 or 10 years in general. They're people that are about to enter the workforce, and they're going to be in the workforce for 20 to 40 years. And so visionary, far-reaching technology programs, innovation and creativity, are things that pull them into engineering and science in general. Thank you.
Please.
Well, I would agree with all of that. Engineers and scientists want to think about the future, and they want to work on things for the future. So our missions automatically inspire people to want to go off and do that. But specifically, some things that we're doing today to help work that is we have a suborbital program with sounding rockets and balloons as an example. It's not strictly the technology part, but it gives students and graduate students, undergraduate students, an opportunity to develop an experiment, test it in a real flight type environment where there isn't the overwhelming pressure to succeed as you would have with a mission. So we find those opportunities, and in any technology program we would do, we want to engage, and in fact any technology program we do today, we do engage universities as well as industry, but in particular the universities to get the graduate students and the undergraduate students engaged in these activities, and in some cases even high school students.
That's interesting. Dr. Colladay.
NASA has a mission that in itself excites people, and so in many respects you have one of the easiest jobs I can imagine to generate the kind of enthusiasm that will lead people into engineering careers and science careers. There's two things that in it starts very early. There's at a young age. There's two things that seem to be in our genetic wiring. Kids love dinosaurs and they love space, and NASA can really capture the interest in space because they have real interesting problems to solve. And in many respects, defining those problems and then translating them into technical solutions is what engineering students and scientists like to wrestle with. So I think the mission is there to generate that kind of excitement.
Thank you, Dr. Colladay. The chair is going to recognize Mr. Olson.
There we go. Thank you, Madam Chairwoman. I have a question for Dr. Braun and Dr. Colladay. Your report provides good insight into the demise of NIAC, but given its unique role and relatively small costs, why was NASA so indifferent about NIAC's fortunes? Why was it allowed to close? Where were its advocates, and why did they fail?
Well, I can only give you my opinion on that, and I'm happy to do so. I of course, wasn't in NASA at the time. What happened with the NIAC is that it was envisioned originally as a cross-cutting program outside the mission directorates that was seeking advanced technology and infusing them into NASA's missions. With the dissolution of the aerospace technology enterprise at NASA, the former CODAR, in 2004, NIAC got moved into the Exploration Systems Mission Directorate. And shortly after that, with the budget crunch, if to use my words, with the budget crunch to get the Constellation program going and getting humans back to the moon, a pretty strong effort was made throughout the agency to squeeze down and remove many of the technology development programs, not just the NIAC. I'm fairly certain that nobody within NASA went directly after the little $4 million NIAC program. But in sweeping out a lot of these larger technology programs, NIAC was also removed in 2007.
Dr. Colladay?
Well, I would agree with that observation. I would also say that protecting the resources for really innovative, far-term, advanced technology requires a champion. It requires a person that has enough stature at the table in the budget battles that come every year to defend that investment, because at the end of the day, it's a good faith investment in the future. And if that advocate, that champion for advanced technology isn't at the table, it's pretty hard in budget crunch time with scarce resources, as NASA has faced over the recent years, to defend a program, even though it's only $4 million. It's every little bit is important.
Thank you for those answers. And I have a question for you, Mr. Scolese. In your statement, you highlight a number of technology development activities ongoing across the agency's mission directorate. But I noticed there were no mention of Ares, Orion, or Constellation. And for the record, could you describe 2 or 3 technology development activities associated with our future manned spaceflight program?
Certainly. There's actually a number of activities that are in what we term our Exploration Systems Mission Directorate, which is where the Constellation program is with Orion and Ares and the ground systems that support that. Some of the far-reaching technologies that we're looking at there that can help not only human spaceflight but others. One is a composite crew module, and that may sound a little different, but most of everything that we have manufactured for human spaceflight has been made out of metallics, aluminum or steel of one type or another. And there's certain benefits if we could go off and use structures that are made out of essentially plastics. However, we've been using them on the science missions for many years because they give us certain benefits that allow us to make those missions much better. But we haven't applied them broadly to large structures because we haven't been able to find any theory that tells us how to build them. So we decided that we needed to go off and understand that technology and develop that technology, and chose to build a crew module very similar to Orion out of a composite structure. We worked that with all of our NASA centers, basically because our science centers have lots of experience with composites. Our Langley Research Center has worked on composite structures for aircraft elements. And Marshall Space Flight Center has worked on composites for rocket parts. And you can go around to all of our various centers that have analytical techniques. But we needed to be able to go off and build it. So we went off and worked with industry and academia to build it, test it as a pressurized system, and we're in the process now of testing it. The good news is, as we're developing a theory, our tests are now going to see how well we did with that theory. The good news is, so far, with the initial tests that we've done, theory and application are turning out to match very closely. So that's very good. Applications are probably not for the crew module, probably not for Orion, but downstream if we want to send people to Mars or the moon or libration points, wherever it may be, will allow us to make structures that are more efficient, perhaps lighter, and better understood. It has commercial applications. Already the aircraft industry is looking at what we're doing and talking about large fuselages as opposed to just segments of the fuselage or the wings. So it's proven to have it's a very good technology. Another area, to follow on with what Dr. Braun said, is going to Mars. Ultimately, we want to send humans to Mars. And as Dr. Braun said, all of our technology is based on the 1970s when we went off and did Viking. The Mars Science Lab is the largest thing we're going to land on Mars, and we are struggling with the fundamental physics of being able to get that done. So what we've done, partnering with all of our mission directorates, is we've instrumented that spacecraft so that we can get some really good data, finally, on the atmospheric profile and what actually happens as we're descending through the Martian atmosphere. In addition, if you look at MSL, it's about the same size as the Orion capsule. So we're also going to use that in helping to improve the design of the Orion capsule as well. So those are just two examples of what we're doing in or associated with the Constellation program.
Thank you for that answer. I mean, those are pretty impressive examples of what we're doing with that technology. And finally, I'd just like to close one question for all of you. What percentage of the NASA budget should be devoted to non-mission-oriented technology development, in your opinion, humble opinions?
Somehow I knew that question would come. And I have said in a number of different forums that I thought an advanced high-tech agency or any organization with a mission like NASA should fence or protect the resources at the level of about 10% of the total budget for really advanced, innovative technology development. Now, the fuzziness comes in how much of that is really near-term, mid-term, and far-term, because technology development needs to be mission-specific in the mission directorates as well. But I would say a good starting point in answering that question would be 10% of the budget, at least building to that. And that includes aeronautics, too. I mean, I'd put the space technology and aeronautics together at 10%.
Thank you, Dr. Colladay. Dr. Braun?
Yeah, well, I agree completely with Dr. Colladay's assessment. In my written testimony, I suggested that at least 10% of NASA's budget to support technologies required to dramatically advance entirely new aeronautics and space endeavors. And so the way I view this question is that that's 10% above and beyond mission-focused technologies. NASA obviously needs to be doing mission-focused technology development work. The examples that Mr. Scolese gave are excellent examples of that, and that work needs to continue. But in addition to that work, which could be jointly funded by the mission directorates and a cross-cutting technology enterprise, in addition to that work, something like 10% of the agency's budget devoted to new endeavors in aeronautics and space is about right for an agency whose goal is to push the frontier and to be looking at the boundaries. Thank you.
Thank you for that answer. And Mr. Scolese, if you feel comfortable answering the question, we'd love to hear it.
Well, you know there's certain questions that I have to kind of dance around a little. This is one of them. Clearly, it's hard to disagree with what was said. A research organization like NASA doesn't need to invest, and we do, and we have to determine those priorities in conjunction with you and the administration. What I can say, though, on the very positive side is that in our aeronautics area, most of that budget is research and development. You can see that sort of with that figure that was shown earlier. In our other areas, we have to go off and look, and the pressures of the mission often do cause some issues. But that's exactly why we went off earlier this year to start looking at what we can do, how can we organize, and how can we find a better way to go off and advance technologies.
Well, thank you very much for your answers, and Mr. Chairman, I yield back my time.
Thank you. Thank you, Ranking Member Olson. And Congresswoman Fudge, would you have some questions?
Thank you, Mr. Chairman. And thank all of you for being here today. I just have a couple of questions. The first one for any of the panel members. NASA's funding for research and technology for spacecraft systems for future missions has been significantly reduced over more than a decade. The summary report of the review of U.S. Human Space Flight Plans Committee stated that investment in a well-designed and adequately funded space technology program is critical to enable progress in exploration. NASA's science mission also requires significant advancements in spacecraft technology to enable exciting new missions. What increases in funding in critical areas such as power, propulsion, communication, and other technologies is needed to assure that these technologies are developed to support future missions? And in conjunction with that, how will the research and technology funding be managed and dispersed?
Well, I guess I got voted. All of those things are critical for both, as you said, both the human space flight and the robotics missions. It's hard to say how much and when. I can tell you that we're looking at all of those areas today, and perhaps give some examples of what we are doing, and that should probably lead to areas of further investigation. Clearly, in communications, we are very limited. We're limited in terrestrial communications because the bandwidth is being used for other services. So we're moving towards optical communications. And in space, that's pretty easy. You don't have to worry about an atmosphere. You don't have to worry about clouds. So we're making an investment in optical communications that will allow us to get more data back in a way that will be more stimulating to the public, for sure, but also get more for the scientific community. Today at Mars, we have a fleet of satellites in orbit around Mars and on the surface, and we cannot bring back all the data because we just do not have enough bandwidth with the RF, with the radio frequency links that we have. So this is an area that we're spending a lot of time in. Propulsion, if we're ever going to get humans to Mars, if we're ever going to get our probes to the far reaches of the solar system efficiently, we need better propulsion techniques. Some of those we're working on today. Ion propulsion is an area that we're now relying on. We use it from the early days in our communication satellites, but we're now relying on it for space missions. The Dawn mission that's going to the asteroid belt is entirely dependent on ion propulsion. And that's a very efficient propulsion that's being developed with industry, but at principally the Glenn Research Center and the Jet Propulsion Laboratory. And it's now been adapted by some universities to go off and do missions. So those are just a couple of examples, but you're exactly right. We can go further in each of those areas to go off and find newer technologies and developments of technologies that will enable those missions. I could add life support, having humans live. Today, we have humans that can spend 6 months on orbit at a time, but they're close to the Earth. If things really get bad, for whatever reason, they can come home. When we start sending humans certainly beyond low Earth orbit, but even beyond the moon, we need to have systems that will keep humans alive and be reliable for hundreds of days to years. And those are technologies that we're all looking at and can do more in.
Thank you. My last question. NASA's in-house research and technology expertise has been instrumental in both assuring advancement of critical technologies and supporting their demonstration and utilization in NASA missions. These capabilities at NASA centers are essential for effectively managing NASA's technology portfolio. It is also needed for developing and effectively leading partnerships with industry and universities. What is and can be done further to ensure that these in-house civil service capability is maintained and strengthened, particularly in light of reduced center civil service complements over the past several years and an aging workforce with a high percentage of retirement-eligible personnel?
Well, certainly having exciting programs, what be they technology or missions, is something that's critical. We believe we have the legislative authorities and the contracting tools to allow us to partner appropriately with industry. And some examples you have, again, on your desk of areas in aeronautics where we have some very strong relationships with companies and other organizations. On those, we can generally speak only in terms of the general benefit because those companies want to maintain their competitive advantage. In the space arena, it's a little more obvious because there aren't as many organizations that are involved there. But I think we have some good partnerships there. I think if further, if you look at our Innovative Partnership Program, what we call IPP, where we do a lot of work with the small business community, we have a lot of examples where we've gone off and actually transitioned the technology to other areas. One example is an endoscope that's used in heart surgery now. Is a spin-off of a NASA activity that we went off and worked ultimately with a small business on. So those are just some examples of some areas that we can do.
Thank you, Mr. Chairman.
Yeah, okay, thank you very much. Just for anybody in the panel here, what's the situation where we're doing research, the federal government's paying for this research, and who ends up with the patents for new discoveries?
Well, unfortunately, the answer is it depends. For things where there's clearly the government is the lead on it, the government owns the patent on that, or of course the credit for the patent goes to the individual that developed the technology. And depending on the agreements that are made, if it's done in conjunction with a university or if it's done in conjunction with a industry, however those agreements are worked to and where the majority of the activity comes determines who the patent owner will ultimately be.
Do you think that the taxpayers are being well served and represented in those negotiations as to who owns, if we finance research, meaning the taxpayers finance research, should we not demand that we have the financial benefit, meaning the patent benefit from financing that research?
Well, yes, sir, and that's what I was trying to get at. In some of our cases where we have agreements, it's only for them to use our test facilities, not to go off where we're putting in resources and they may reimburse us for those test facilities. So that's why I was getting at, it depends. If the government funds it, we own the patent. There's no question about that.
Okay, good. That's what I needed to know.
Yeah.
It seems to me that would be a source of revenue that we could utilize when we talk about expanding the budget for people. Maybe we could make sure that we are receiving the benefits from that research. Is there any research being done on the space elevator concept?
I'd have to answer that one for the record, sir. I don't know at this time. I know that there's a prize, or not a prize, there's a technology activity that would allow that to be proposed to, but I do not know what was proposed this year.
Okay. Are we, I would imagine we just had a launch on a hit on the moon to find out if there's ice that we could utilize. Do we have research going on to find out if there is ice on the moon, how we can use that ice to further the space program?
Well, yes, sir, we do, because while we're not as sure about the moon, we are very sure about Mars. We have touched ice on Mars, and we know there's a lot of water there. So we do have activities that are related to what we call in situ resource utilization, where we can take advantage of the resources that are available to us and then go off and use them. And in the case of water in particular, we have fuel cells where we separate the water into hydrogen and oxygen and then ultimately combine it to use it either as a rocket fuel or to use it as a fuel to generate electricity.
Right. Is there much being done on beaming energy, or is that something that we did 10 years ago or 15 years ago and not doing it anymore?
We actually have an experiment that we're looking at for doing on the space station to do that. I don't know what the current manifest is, but low power beaming to get some idea of what we can do there and what the practical limitations are. So it has not gone away. It's still with us.
It would seem to me that that's one thing that people I've talked about this about 10 years ago, I remember, and it just seemed to me that they have a lot of potential, but most other people don't think it has much potential. But if we can beam energy, that could actually enable us to put heavier objects into space because we don't have to carry their own fuel.
Yes, sir.
Let me see, I'm going to mention something about children and dinosaurs and space. My wife and I were blessed with triplets 5.5 years ago, and one boy and 2 girls. And I just wanted to reconfirm that they are excited about dinosaurs in space. So with that said, thank you very much.
Congressman, thank you. Congressman Miller? Edwards, excuse me.
Donna Edwards from Maryland. Thank you for your testimony. I actually wanted to follow up on a couple of things. One is I do think and I appreciate your testimony as to the difficulty balancing long and near-term goals, and I guess there's stuff in between, and investments and strategies in those, because although I think a lot of the public really thinks about NASA as sort of the one place in government where people really are thinking well out into the future, that because of budget and other kinds of pressures and performance pressures, that we perhaps are not looking as much into the future as we need to be, and that means in terms of investment in research and advanced technologies. And so I wanted to actually follow up from Mr. Rohrbacher's question regarding intellectual property and intellectual property rights. Because I think that, again, is a tough balance to strike. If you're trying to, if you want to put out, requests for really innovative research, then, a scientist, a researcher, an investigator wants to have some skin in the game. And part of that skin is potentially that, great patent down the line. And so I wonder if you could comment for me about how we can strike that balance of intellectual property rights and sharing so that we get, the greatest bang for the buck and benefit as taxpayers, but also incentivize some of our researchers to do that cutting-edge, risk-taking, investigative work that we know should continue into the future. And then I'm also very interested to know, on that question, there are technologies and research going on in commercial space flight, in military space, and it seems that there are lots of walls and barriers in terms of sharing that innovative intellectual property that's developed in each one of these spheres that I think gets in the way. For example, if a technology is developed on the military in a space side, then we have, some competitors around the world who are actually using some of those technologies and sharing them and commercializing them. But right here in this country, those same technologies can't be shared on our civilian and commercial side. And that's a real downer when it comes to making investments in research. And so I wonder if you can give me some thoughts about that and what we might think about in the Congress to try to mitigate that.
Certainly. If I can take the last question first, the barriers for us to work with our colleagues and other agencies in the government are not so great. We typically can do that quite well, and oftentimes when you're doing a research or a technology activity, it's not always known in the agencies which ones are there. So we have to have much stronger dialogues, and that is something that I think we're all working on much more diligently now than we have in the past. But even in the past, we had, for instance, a technology, I forget the exact name because it keeps on changing, but a technology working group where our NASA chief engineer and before that our chief technologist would work with their DARPA colleagues and other colleagues in the Department of Defense or Department of Energy to go off and find areas of common interest. Further on that second part, the area where we really find that we hurt ourselves and we could really use help is with the ITAR, the International Trafficking in Arms Regulations, because that really limits our ability to take U.S. developed capabilities and bring those overseas where it could bring benefit to our companies. And even in the government, it's very difficult in government-to-government interactions for us to take technologies that we have and make them available so that it's a U.S. developed technology and a U.S. managed technology. Instead, we develop it, someone sees it, and they'll go off and invest their resources to go off and make the profit.
I have an example of that right in my district.
I'm sure
and that's
you do.
why I ask.
Yes. Well, we both kind of worked at the same place at one point, so I figured that was probably the answer. On the earlier question about the intellectual property rights, it'd probably be better if I took that one for the record and gave you all of the types of contracts that we have. Some have greater liberties for the inventor to go off and have property rights for those, even if the government is funding it. But it depends a lot on what that agreement says. So we have Space Act agreements and contracts and grants, and they're all a little bit different. So why don't I take for the record to get you a summary of what those are and what the intellectual property rights are associated with those various ones.
I'd appreciate that. Thank you.
Okay.
The chair is going to ask a few questions or make a few comments. Really, I think most of my questions have been answered. This visual aid that was produced is absolutely impressive. I would say that you could also put a hospital room with a bed and a patient on this very page, and there would probably be greater than 18 improvements that have happened because of NASA, from the early diagnosis of breast cancer because of the innovations in the Hubble telescope to the miniaturizations of instruments that you mentioned, to many, many things that have happened over the last 2 decades as a direct result of the innovations at NASA that we did not know were going to occur. And that's one of the great benefits of research and development. One of the great benefits of science is that science has to prepare to discover, and then after it discovers further what it did not know was there. I think Einstein said that research is something he does when he doesn't know what he's doing. And so I think we need to really emphasize the fact that research and development, whether it's the discovery of the Van Allen radiation fields, whether it's our continuing effort to improve materials so that we can further discover, whether it be the neutron scattering and the inelastic and elastic properties of radiation in material, is absolutely critical to the advancement of science. And NASA has been at the forefront of that, and I might take just one liberty to say that I think it is the absolute soul of America, both in its intellectual capabilities and equity, and also in America's future. And I appreciate each and every one of you being here. And coming from the Alabama 5th District and Marshall Space Flights, you can see that I'm a little bit prejudiced. But I think Ranking Member Olson has another question.
Thank you, Mr. Chairman. One more question for Dr. Colladay. And Dr. Colladay used to run NASA's Office of Aeronautics and Space Technology. NASA separated those research fields a few years ago, with aeronautics placed in its own mission directorate and space technology placed into the Exploration Systems Mission Directorate. Was that a good idea, or should the two be reunited into a single office? And as a follow-up, would reuniting them strengthen technology development at NASA, or is money the issue, not organization? And finally, would reuniting them suffice rather than creating a DARPA-like organization? I know it's a lot.
Well, there were good and valid reasons for having the two combined when you get to the far-term, long-term based research, because when you're working CFD and advanced materials and the basic navigation and controls and the sort of the basic disciplinary research, and it's a long way from application. The people doing the research didn't always know they were spending an aeronautics R&D dollar or a space technology dollar. They're working on important and exciting engineering and science problems, and so there were a certain number of advantages of having them together. They had to be defended separately. It gave enough critical mass that that person at the table that I spoke of as the champion defending advanced R&D had a big enough portfolio to be at the table. But that's not the only way to do it. There are a lot of different governance models. Whatever governance model you look at, certain things have to have to be attended to, and I mentioned it in my remarks. One is when it's separate organizationally and put together as it was 20 years ago, aeronautics and space technology, you really have to put a lot of effort into making sure that what is being done is relevant. You get criticism that, oh, they're just off playing in a sandbox. That is unfair a lot of times, but it points to the need in an organization that's responsible for advanced technology to make sure they're working with the user community, they're working with the ultimate developers to make sure that what they're working on has a transition path that is relevant, and then that a management approach or a governance model is in place to manage the transition of these great things that come out of the research that have to later be developed. One thing in being a director of DARPA that I learned is, we quit doing the research when we had proof of concept. If we proved that something was feasible, that was enough. We were off doing something else. A lot of work, a lot of hard work and money goes into taking those ideas and putting them to practice. And so it's not enough to develop the technology, prove feasibility, create this environment where it's all right to take risk. You do all those things, and that's important, but the ultimate user and the developer has to run with the early technology development along in parallel to manage the transition. I don't know that on my watch in NASA that we always did a good enough job on those 2 points: relevancy, making sure that the ultimate user was involved, and that we managed the transition from what was old CODAR into application. And the application sometimes wasn't with NASA at all, it was with industry.
Thank you very much for that answer, Dr. Colladay. I see I'm running out of my time. I yield back my time, Mr. Chairman.
Thank you, Ranking Member Olson. I'm reminded before we close that the concept for high-speed CT scanning was available to us 30 and 40 years ago. The coefficients of absorption and expansion, I can remember working out problems with my slide rule and taking me a great deal of time, and it depended on a development outside of the concept of high-speed computing that allowed us to develop the CT scanner, even though we had the concept proven many, many decades before. So I think as pure R&D, pure science begins to develop, we serendipitously discover things over here that apply over here, and we can't always predict that. Before we bring the hearing to a close, I want to thank each and every one of you for being here. And thank the witnesses and also our participants. The record will remain open for 2 weeks for additional statements from the members and for answers to any follow-up questions the subcommittee may ask of the witnesses. The witnesses are excused and the hearing is now adjourned.
Thank you, sir.
Thank you.